Welcome to the demonstration on voltage stability case 2 from Alstom Grid and our partners. While we'll be visualizing the results within Alstom's geospatial operator UI, we are relying on PowerTech's model-based voltage security assessment tool or VSAT as our underlying engine for a comprehensive voltage stability analysis. For this case, we will be utilizing VSAT's transfer analysis and PV and QV analysis capabilities. We use the following assumptions to model the system. Capacitors are allowed to switch, STATCOM can move, ULTCs are locked, loads are modeled as constant MVA. Here we see the test system which we modeled in VSAT. We'll perform transfer analysis by increasing loads at zone 10. This increased load will then be picked up 50-50 by the two generators. Let's take a look at the operator UI. The sink area in this case is zone 10 and the source areas are zone 30 and zone 50. This is our geospatial display. Different kV levels are represented using different colors. On this display, green squares represent substations and the ones with these markers have PMUs installed. Here we see the two equivalent generators and the interface between the source and the sink areas. The real power flows are animated on the transmission lines. The voltage profiles at the buses are also shown as contours, changing color from cold to warm as voltages decrease. On the top we see the megawatt margins, where the bar indicates the utilized capacity with respect to its insecurity limit under the most binding contingency. Right next to it is a summary of the scenario, the operating point, and its limits. At the bottom right, we also show the megawatt and megavar real-time trends. Now that we have taken a look at the different elements in the operator UI, let's walk through this test scenario. At time t equals 0 seconds, VSAT predicts that we are only utilizing 72% of the total n-1 available capacity. The most critical contingency and the reason for the insecurity are also shown. At the same time, based on the measurements, the transfers across the interface are relatively low. At time t equals 1500 seconds, we observe higher stress levels in the system. We can see that the megawatt margins have dropped. Now, 83% of the total available capacity is being utilized. The transfers from the source and sink areas have also increased to 423 megawatts, approximately 100 megawatts more than before. At time t equals 2900 seconds, we see that the stress levels have reached high enough and the maximum available n-1 capacity is being fully utilized. What this means is that if the most critical contingency were to happen, the system would become insecure. The east to west transfers at this point are 893 megawatts. And as time continues to progress, stress levels increase and margins continue to drop. Finally, at t equals 412 seconds, the contingency happens. Line 116 to 120 trips and the system becomes unstable. From the operator UI, we can directly launch the VSAT interface for a more detailed engineering analysis.
created a VSAT case to perform the transfer analysis by increasing load in Zone 10. VSAT is then able to provide all data necessary to perform PV and VQ analysis. This data can then be viewed by clicking here and then selecting PV plots. Once the data is selected, we can then click the plot button to view the PV curves. This plot shows the voltage at bus 113, which is located here. In this curve, we also see two jumps located here and here. These show the effects of capacitors being switched in and boosting the voltage upwards. Now we will illustrate the power stability margin at various times. At time 0, the load is 432 megawatts. And we can see that we have 920 megawatts of margin before hitting instability. At time 1500 seconds, Zone 10 load has increased and now the margin has decreased to 792 megawatts. At time 2900 seconds, the margin is now 220 megawatts. And finally at time 4000 seconds, there is a 200 megawatt margin before hitting instability. VSAT can also perform QV analysis. This analysis will be performed at bus 113 in the pre-contingency condition. We will perform computation at 3 points. The first point will be at the base point. The second point will be at near instability, and the final point will be just before instability. So we begin by plotting the QV curve for the first point, which is the base point. Notice we have a relatively large margin of 311 megavar. Now we move to the second point, which is near instability. As expected, the margin is now significantly decreased to 35 megavar. Lastly, we move to the final point, which is the point just before instability. Here the margin is essentially zero, indicating instability is imminent.
In conclusion, what we have shown you is our advanced operator visualization coupled with PowerTech's model-based VSAT analysis offering predictive capabilities from base case conditions. And finally, our findings.